previous lecture, we introduced the quantum mechanical formulation of kinematic quantities by Heisenberg, and we said if there is a quantity xt, it is represented by a collection of numbers C n, let us say n minus alpha, and the corresponding frequency omega n, n minus alpha, and the time dependence of C n, n minus alpha is given as e raised to I omega n, n minus alpha t. This collection of numbers gives this. There could be another quantity yt which can be represented by collection of d n, n minus alpha omega n, n minus alpha, and there I said that xt yt is not equal to yt xt. So, what I should say is not necessarily equal to. For example, if I have xt and multiplied by xt, that would obviously be the same if we change it, right. But the way we calculate the representation has become now matrix multiplication, and what we want to do in this lecture is obtain the quantum condition in terms of these numbers C and omega. That is our goal. So, again we will be going back to the correspondence principle, but before that let us now look for the time being differentiation in classical and quantum domain. We have been doing it, but now let us explicitly say it. Classically, the quantum number n is very large, and therefore, we can afford to do differentiation, and which is the same as delta E, suppose this is dE by dN by 1, because delta n, which is 1, is much smaller than n in the classical regime. In quantum mechanics, this dE by dN would not be possible because numbers are small. So, in quantum mechanics, n is small. So, any differentiation in classical sense must be replaced by difference. That is how we distinguish between the two. So, for example, recall that omega alpha omega n was equal to alpha d by dn E in classical domain, that means n tending to infinity. In quantum domain, alpha d by dn will go over to E n plus alpha minus E n. That is the difference, or E n minus E n minus alpha divided by 1, because the delta n is 1. This is the difference when we make a transition from classical to quantum. Quantum, it has to be differences, and alpha d by dn is going to be this difference, where the two quantum numbers differ by alpha, and we are going to make use of it. That is why I wrote it. Now, recall that the quantum condition that gave us results before Heisenberg's paper was this condition: P dx equals nh. So, first thing Heisenberg said, do not keep this in integral form. Why? Because this P dx could be nh plus some constant, and we do not know this constant, so it should be replaced by a differential form. And therefore, what he said is replace this by taking derivative with respect to n on both sides, p dx equals h. And once you integrate it, that constant may come out, which would basically, in quantum mechanical sense, this would mean that integral p dx for n minus integral p dx for n minus 1 is equal to h. This is what he first replaces the quantum condition by. And now we are going to derive this in terms of c and omega. So let us do that now. So when we write p dx in the n tending to infinity regime, you see, again we are going to make use of correspondence principle. I will derive some results from n equals infinity and then immediately translate them to quantum mechanical language, and that's the use of correspondence principle that Heisenberg made. Is going to be equal to mass times v square dt over a period, which I can also write as mass integral 0 to t v square dt. That's the action. So let us evaluate this. Is still in the n tending to infinity regime. xt is summation, let us write it alpha c alpha e raised to I alpha omega, which depends on this n t for the nth level. So v, this is nth level, t is going to be equal to summation alpha I alpha c alpha e raised to I, and there is omega also, alpha omega, which depends on n t, that is v alpha v t. So v square t is going to be equal to summation alpha summation beta I alpha c alpha omega n times I beta c beta omega n e raised to I alpha plus beta omega n t. And when I do integration 0 to t v square t dt is going to be summation alpha summation beta. I can write this as minus alpha beta c alpha c beta omega square for the nth level e raised to I alpha plus beta omega n t dt 0 to t. And let me remind you, this t is nothing but 2 pi over omega n, the period for the nth orbit, for the lowest frequency. All the other are the harmonics. And therefore, this implies that integral 0 to t e raised to I alpha plus beta omega n t dt is going to be equal to t for alpha equals minus beta and 0 for all other alpha and beta, because in that case e raised to I alpha plus beta omega at capital T would be same at 0 and t, so that is the period. And only when alpha equals minus beta or beta equals minus alpha, then this quantity becomes 1, and therefore the answer becomes capital T. And therefore I can write integral v square t dt 0 to t is equal to summation alpha, beta is now replaced by minus alpha, so this is going to be alpha square omega square n c alpha c minus alpha t. That is all. And 1 omega and t multiplication gives me 2 pi, and therefore I can write this as 2 pi summation alpha alpha square omega n c alpha c minus alpha. That is the classical result. So in the limit of n tending to infinity, integration p dx comes out to be, there was an m also there, so I get 2 pi m summation alpha square omega n c alpha c minus alpha. All right. Now I need to, that's the classical result or n tending to infinite result. Now I need to translate this into quantum result. And not only that, I need to write d by dn of integral p dx is equal to h. So let us write that. If I do that, d by dn of summation alpha 2 pi m I can write outside, alpha square omega n c alpha c minus alpha is equal to h. Now I am going to make use of the correspondence principle. So I have 2 pi m d by dn of summation alpha square omega n c alpha c minus alpha is equal to h. When I do quantum mechanics, what does this mean? Remember, c alpha and all these things are corresponding to the nth level. So c alpha, let me write each number separately. C alpha would be c n minus alpha. C minus alpha would be nothing but c n minus alpha n, which is same as c star n minus alpha. We have done this in the previous lecture. And from here I am going to take alpha omega n as omega n minus alpha. So when I translate, I will be very careful in this. I will write 2 pi m d by dn of summation alpha, one alpha remains. In the brackets I am going to have omega n minus alpha modulus of c n minus alpha square is equal to h. Now recall that I had done something with what alpha d by dn means in quantum mechanics, and I am going to use that now. So I am going to write this as 2 pi m summation alpha. I can take d by dn inside because that is operating only on the brackets, square brackets. So I am going to write this alpha d by dn omega n minus alpha modulus of c n minus alpha square is equal to h, and this is nothing but difference over alpha. So I am going to write this as 2 pi m summation over alpha omega n plus alpha n c n plus alpha n modulus square minus omega n minus alpha modulus c n minus alpha square is equal to h. Alpha varies from minus infinity to plus infinity. So let me rewrite this. So the quantum condition comes out to be 2 pi m summation alpha equals minus infinity to infinity omega n plus alpha n modulus of c n plus alpha n square minus omega n to n minus alpha modulus c n minus alpha mod square is equal to h. I can do even better and write this as 2 pi m summation alpha equals minus infinity to infinity omega n plus alpha n c n plus alpha n mod square minus 2 pi m summation alpha equals minus infinity to infinity omega n minus alpha modulus c n minus alpha mod square equals h. I am going to change the second term. This term I am going to replace beta by minus alpha and write this as summation beta equals infinity to minus infinity is the same thing, whichever order you run it in, omega n plus beta modulus c n plus beta whole square, which I can write as summation beta equals minus infinity to infinity omega with a minus sign. I will change the omega n plus beta n modulus c n plus beta n mod square. I could do this because omega n plus beta is minus omega n plus beta n, and c n plus beta n modulus is same as modulus c n plus beta. If I switch the two, right, it does not really change whether the transition is from n to n plus beta or n plus beta to beta. And therefore, I can write this quantum condition also as 2 pi m summation alpha equals minus infinity to infinity omega n plus alpha n modulus c n plus alpha n square, and the second term comes from the other term. So, it becomes, instead of 2, it becomes 4 pi m equals h. So, we have all these cn's and omegas, we have the quantum condition in terms of them, and now we need to apply these conditions to calculate c and omega, which we will do in the next lecture.